Okay, everyone, let's get started. Any questions about the lab? Any issues? So my plan for today is to finish up the Verilog material. I was hoping that we could assign the next lab today, but I think we probably have one more lecture left of Verilog. So in the lab this week, you'll have the chance to do your demos for Lab 2. Make sense? Okay.
Sorry, you're saying this is upcoming lab or next after demo?
Lab 2.
Okay.
So Lab 1, you didn't need to demo that one because we have an auto grader. That's the RISC-V code that does the square root. Lab 2 was the 7-segment displays, which I think probably most of you didn't find that to be too difficult, but we want to make sure that you've got it working on the board and you can demonstrate it.
Okay.
So that's what the demo is for.
And that'll be this week or next week?
This week,
Okay.
yeah. So just get the TA's attention sometimes this week and demo it. So the way it works is that it was due on Sunday. So as long as you uploaded it to Dropbox by Sunday, you're good. You've submitted it. But we won't be able to assign a grade for it until you do your demo, right? And so if you don't get to the demo this week, that's okay too. But we'll have the lab time this week for you guys to demo. Just because I don't think I'm going to get far enough to assign the next lab yet. Okay? So if you look at the schedule, I had it marked as microarchitecture. That's the next topic, but I want to finish up SystemVerilog today. I've got another quiz, though, that is due on Friday on SystemVerilog, so make sure you take that.
It is Friday. It's on the schedule. It says the title of the quiz is Take by 9:30. Schedule says.
Oh, right. Yeah. Sorry, that's a typo. Yeah, thank you. I'll fix that. The quizzes, I always have the quizzes due on Friday. So speaking of quiz, let's look at the first quiz. So the first quiz said, consider the following C code and its translation to RISC-V assembly. What instruction is missing? So you've got high-level code here on the left, which is a C for loop, and the RISC-V assembly on the right. And the question is, which instruction is missing? In order to answer this question, you have to figure out how each of these RISC-V assembly instructions relate to the C code. So the first instruction is load address of A into X11. So that's setting up a register, YX11, or not X11, X1, YX1, that just was chosen, that was allocated for this purpose, and it's being loaded with the address of A. So in C, that would be equivalent to saying, X1 is getting ampersand A, address of A. Now you'll notice that's not in the C code because the C code doesn't require you to explicitly do that, right? Although A is declared as an array, so I guess A in C, arrays are pointers. So technically A in the array is the base address of the A array. Okay, so then the next line loads the constant 40 into X10 with a load immediate instruction. And that's the loop limit, which is 10. Why 40? Why 40 and not 10? Because, so in C, an array index is automatically multiplied by the size of the elements that comprise the array, but in assembly, it doesn't do that, right? So what I'm doing here is I want to use one register to keep track of the loop and also serve as the index, the offset into the array for the A array. So I'm doing this shortcut, which is to multiply the values in I by 4, which is the size of an integer. You guys with me? Now you might say, wait a second, you never said that A was integers. No, but it's implied by the code, right? Okay, so, and by the way, integer being, I shouldn't say integer anymore because integer could be 64 bits. It's a 4-byte integer, right? 4 bytes per element. Then we load 8 into X2 because that is going to be our initial value for I, so it's 2 times 4 is 8. When we start our loop and there's a blank instruction, and then we subtract one or rather 4 from I and put that in x3. Why? Because of this. So we're getting ready for this a of I minus 1 reference. So I subtract 4. So I'm setting up this address. And then we add x3, which is the offset into the A array, with x1, which is the starting point of the A array. So now x4 is now the calculated address of A of I minus 1. So then we load that, and then we decrement x4 by 4, which is going to give us the offset for I minus 2 in the A array, right? Now this part's a little clumsy because I'm taking x4, which was my previously calculated address for A of I minus 1, and then just subtracting 4. A compiler would never do this. This is something, this coding style is only because it was a human being writing the code, right? A compiler would have done this differently. But then x4 is the address of A of I minus 2, then I load that, then I add those two things I loaded, which are now in x5, x6, put the result in x5, so I recycle the value of x5. And then I add x4 to x2, right, which is the loop counter, and then I branch back up to the loop. Make sense? So what's missing here? Well, the branch back to loop is unconditional. So we're missing a condition to see if we should keep looping, right? And so that would be we need to check to see if I is less than 10, right? Now I just noticed actually that I'm missing a second thing in here too. Because I also need to, after I add these two guys together, right, which I do in this instruction into x5, that should be stored to A of I. And apparently I'm missing that as well. I just noticed that now. But anyway, that wasn't an option in the quiz. The option there that you want to pick is branch greater than or equal to x2, which is our I, less than x10, which is our limit for the loop, right? And so we're going to branch to exit. Now notice it's branch greater than or equal, which is the opposite of less than, because this branch is going to take us, is checking to see if the loop is done, right? So it's the logical complement of the loop continuance condition. Make sense? Everyone with me? Okay. Any questions about that? Okay. So what does the following code perform? It's 2 shift left, shift right, and an OR. So this is a kind of a bit manipulation thing where I'm taking x3, the lower 16 bits of x3 are being moved into the upper 16 bits of x2, right? Shifting in 16 zeros that'll come in on the right-hand side. Then you take x3 and shift the upper 16 bits to the right-hand side with a shift right, and then you merge them together with the OR. So the effect of this 3 instruction sequence is it's swapping the lower half and the upper half of x3 and putting the result in x2. Make sense? Okay. What are 2 operations that you can perform on SystemVerilog code? Simulation and synthesis. That's the only 2 I know of. What is the problem with the SystemVerilog module below? In this case, this is something that might not be obvious to you now, but once you learn SystemVerilog, it will become very obvious that this is a condition where you're double driving Z. You've got 2 circuits that are trying to set Z, which is not allowed. But in any other programming language, it would be no problem at all. But in Verilog, it's no good because you've got 2 logic gates that are going to be setting Z, and they'll potentially be in conflict. Now, if I remember correctly, if both of those statements are setting the same value to Z, then the simulator will actually just show you that value in Z. The only time you'll detect this problem in the simulator is if both lines of code are, one line of code is setting z to 1 and the other one's setting it to 0, in which case you'll see x. But if they're both setting z to 1 or both setting z to 0, you'll just see that value. On the other hand, though, if you go to synthesize this on the FPGA, I believe you'll get an error. It won't synthesize that. It won't let you blow up the chip. Because if you synthesize this and then you downloaded this bit stream to the FPGA, you would be creating an internal short circuit in the FPGA, which would, if they're in conflict, would sink a lot of current, right? And heat up the chip, possibly burn it out. Okay. However, let me skip ahead because I had another question. Yeah. However, in this case, though, this is another case where if you have two statements that both assign A, but one of them is setting it to Z and the other one's setting it to 0, in this case, you're okay because the first statement is, they're both setting A, they're both driving A, but the first one is driving it to a high impedance state, right? A floating, it's kind of disconnecting. So actually, this is okay. And if you do this, the value you'll get for A would be 0 because the 0 would override the Z because the Z is saying, essentially, don't drive A, right? So if you set a signal to Z, you're saying don't drive it, don't set it. I've never tried this actually on an FPGA though. I think there are tri-state drivers on FPGAs, but I've never tried to do that. I don't think I've ever actually deployed any code on an FPGA that set Zs for anything. This is more common for an ASIC design. Okay. Does SystemVerilog support structural or behavioral HDL? Both. And how many possible values can be assigned to type logic? In this class, 4. Although in reality, in SystemVerilog, they actually have other values, but they're all variations on the values that we already talked about. They're different driving strengths. So there's a strong 1 and a weak 1 and a strong 0 and a weak 0. But the 4 basic things that you can assign to logic is going to be 0, 1, X, and Z. Okay. VHDL has a few more, actually. VHDL has a dash, like a hyphen, which is a don't care, and it has a U, which stands for undefined. Verilog uses X for multiple reasons. It uses it for don't care, undefined, and conflict, which I'm not really, that's one thing I like better about VHDL is they have a little bit more specific values for those things. Okay, now this question's kind of tricky because here we have two modules. There's a top, which instances my thing, which is of type bottom. And the question is, what's the value of A and Y within my thing? Well, inside of top, we have an input A and an output Y. The input is being set to Y, which is set to 1 here. So A is going to be 1 inside of bottom, right? And then Y is the complement of A, so Y is going to be set to 0, right? Make sense? Okay. Assume the following SystemVerilog code. Oh yeah, we were talking about that. How many bits comprise the signal A? It's going to be 4. 3 down to 0. Now you might say, well, that's kind of easy. Yeah, but you have to remember that the number of bits is the number on the left added with 1, right? So it's 3 down to 0. So it's 4 bits. You might wonder what happens if you say 0 up to 3, 0:3. No difference. Makes no difference. It doesn't reverse the bits or anything like that. It makes no difference. Yes?
I tried that. I remember that I was writing it, I think in Lab 2, in like one of the modules that put like, I don't remember how many bits it was, but like 0, 3, and then I entered them in decreasing order. That makes any sense. That I put it, defined it.
Oh, when you set it?
Increasing, but I set it in decreasing order.
Yeah. Oh, okay. Yeah.
I was wondering, like,
I don't know. I'd have to see it. I'm not sure. I think I tried it once, but it's been a while.
It's something like they have to be the same way or something.
Yeah, I mean, I can tell you that I don't think I've ever read anyone else's code where they have the smaller number first in the range.
I was just seeing what
Yeah, yeah. Yeah, well, that's good. That's good to try it. And then to what value is A set in the SystemVerilog snippet below? This is a kind of a deliberately complex statement, but in here we've got a trinary or ternary. Is it ternary? Ternary operator. And remember, the ternary operator is evaluated last. It has the lowest precedence of any other operator. So then the question is, well, which one has? I mean, now we have left shift and equals equals. Which one is done? Which one is evaluated first? I don't even remember. I never remember this. I have to look. Yeah, I don't know off the top of my head which one is first. I got to go. Here we go. Equals. Oh, shift is above that. Yeah. Okay. So shift happens first. That makes sense. Okay. So the shift is going to happen first. So we're going to take 2, shift it 1 bit to the left, which will multiply it by 2, right? So that'll become 4. And then we want to check to see if it equals 4, which is true, in which case the whole statement will evaluate to 1. Now, the only thing that's a little weird here, though, is the problem is that this is a 2-bit signal, and we're shifting it by a 1-bit signal, and then we're comparing it to a 3-bit signal. So if the result of this is a 2-bit signal, then the answer is not going to be 4, it's going to be 0. Because you don't have enough bits in 2 bits to hold the value 4. So it may actually end up being 0, depending on what is the value of this intermediate expression. Is it going to be 4 or 0? Well, the answer is 3 bits. So 1. I guess I tested it.
The assembler pads.
Yeah, apparently it's going to assume that it's going to have to add an extra bit to this. So 2-bit signal shifted by 1 bit to the left gives you 3 bits. Yeah. I assume I tried that. I've had these questions for a little while. Okay, and then here's another question where we have some structural code mixed with some behavioral code. So what value is A set to? Which A? This A? This A. Right. So A is declared here. It's assigned here. But then it's used here. Now, this is a problem because if you look at where they plugged A in, A is plugged into Y, and Y is an output, right? So what's happening here is that we're assigning A here, but we're also assigning it here. Make sense? So this is being double driven. Well, it's being double driven, and it may be in conflict. Is it in conflict? So A is 1, and then this my thing is going to take 1 as an input and invert it and give you a 0, right? So this thing is going to set A to 0, and this assign statement is going to set it to 1. So this will give you an X for sure. Make sense? This is a little irritating to me because it's not clear from this line of code that A is being set, right? Because Y is being used as an input. Y is connected to an input and A is connected to an output, but that's not obvious. You wouldn't know that unless you drill down into bottom to see what's going on in there, right? There's nothing here showing what the inputs and outputs are when you instantiate the module. That's only listed inside the module definition. So you have to go into the module definition to figure out what's an input or output. You don't see that here. So that's, I don't know, I don't like that. Of course, there should be comments in here indicating that. Okay, everyone see that? So the point of this question is that you have to keep in mind that you can assign a signal either through behavioral or structural code. So this is a structural statement, and this is a behavioral statement, but they're both fighting over A. Okay, that's all the questions for that quiz. And don't forget to take quiz 2. It's got some more Verilog questions. Okay, so last time we talked about a lot of stuff. I went really fast. I covered the always statement. And the always statement is used for multiple things. It's used for sequential logic, which is any kind of logic that has memory in it. So that would mean flip-flops, latches, and rams. Flip-flops, latches, and rams are the 3 kinds of memory, all of which are made with an always statement, or I should say described with an always statement. We also use always statements for combinational logic if you want to use an if statement or a case statement or a for loop, which it's pretty rare to have a for loop in Verilog code, but you can put it in. It gets unrolled. So it's really just kind of a way to copy and paste code, basically. In other words, for loops are unrolled statically when you compile Verilog code. But the point is if you want to use any of the constructs that you're used to in high-level languages, you have to use an always. Like I said, I usually stay away from doing combinational logic in an always statement unless it's really complicated, like the control unit that we're going to do as part of our RISC-V processor, which I'll have a bunch of nested if-then-elses. Okay? And then also, always statements are needed for test benches. So we use them for writing code that's not meant to be synthesized. It's meant to march through test vectors to test the design under test, right? So there's a lot of things. It's really versatile. I also mentioned that in Verilog, the syntax of an always is just always at sensitivity list. That's the only way to build an always statement in Verilog. The problem is that this was seen as a problem with Verilog because when you write always like this, you may accidentally imply that there's memory when you didn't need to. So they introduced these alternative ways to write an always in SystemVerilog. They added the always underscore FF, the always underscore com, and the always underscore latch. And then there's the one that just is always. It's only for non-synthesizable code. I think that's always been in Verilog, right? So always underscore com you would put in if you explicitly want to make combinational logic. So that would be used for your control unit and muxes and things like that in your CPU. The reason why you would use that is that if you accidentally put memory in there, it'll give you an error when you compile. So it's a safeguard for you. You guys with me? Now the alternative is you just say always at star, which is equivalent to always comb. Right? Then there's always underscore flip-flop, which is only for edge-triggered memory. So if you do always underscore flip-flop and you accidentally put a latch in there, it'll give you an error. Okay, and I'll talk more about latches versus flip-flops here in a minute. So there's different styles. In this class, it seems like half the class uses this one, even though I don't really teach it. I don't know why. I don't know if people are using ChatGPT or reading stuff online, or I don't know. But even the textbook doesn't use this. The textbook that we have in this class uses the SystemVerilog versions of the always. But I don't care which one you use. It doesn't matter. Like I said, these are just designed. These other ones are they're designed to protect you. Okay? All right, so let's look at some examples. I already talked about this. So I'll just do this quickly. So here's an example of an always com where we have an if statement, right? If then else. In this case, the always statement is just implementing a complex assignment statement in the sense that anything that's assigned, anything that's on the left hand of an assignment is an output from this always and therefore is being driven, right? So this always statement is going to control anything that's being said in here. So you don't want to set it anywhere else or you'll be in conflict. Anything that's treated as an input, meaning that it's on the right-hand side of an assignment or it's used in a condition, like an if condition or a loop condition, is an input. So anytime any of those inputs changes, it activates this guy, activates the always, right? So the sensitivity list, in other words, is automatically inferred from the code. You don't have to like list all the signals that the thing is sensitive to. So just make sure though that you assign, anytime this guy activates, you want to make sure that it assigns all its outputs or you'll end up with a latch. You'll end up with memory. So let me skip ahead a bit and talk about that in a little bit more detail. Okay, so in Verilog, if you want to have memory, you have to use it always. And within the always statement, there are two ways that memory is inferred from your code. The first is if you have inputs. See, in this case, we have an input B. Why? It's an input because it's on the right-hand side of an assignment. But I don't have B in the sensitivity list. I just have pause edge clock. So because I have an input that the always statement is not sensitive to, then automatically now I have memory. This is sequential logic. And because it's pause edge clock, this will end up creating a flip-flop. Okay? But there's another way. This one's a little bit more insidious. So if I have an always at star, okay, so this is another way of saying always underscore com, but I don't assign the B if A is not 1. Right? So I have an if statement here, but I don't always assign B depending on the outcome of the if statement. So in other words, in this case, A and C rather are inputs, right? Because A is in the condition and C is on the right-hand side. A and C are my inputs and B is my output, but A and or C could change, activating the always, but then B may not get written. So this creates a latch because it's not level sensitive. Now, if you had said always com and you try to compile this statement, you get an error. But if you use always at star, which is equivalent to com, it would compile, it would give you a latch, and you may end up, generally you don't want latches in your code. I've never had a case where you'd want a latch. You should always have flip-flops. Latches complicate the timing analysis. So if you do put latches in, FPGAs can implement latches, but you'll find that your clock speed will be very low if you do that. Right? You won't be able to, it'll be slow. In fact, in this class, if you have latches, it may not even be able to run at 50 megahertz. It may not meet time enclosure at 50 megahertz. So this is a bug, right? This is a bug. What you should do to fix this bug is you can either put an else here, right, with assign B in the else, right? Or you could add a statement at the beginning that assigns a default value for B. Those are the two ways you can get around that. Okay, so what I mean by latch? Did you guys talk about latches in 2.11? Okay, so I'll just go through this really quick. So here, let me give you, so we have a clock. In this case, we have a clock and we have a value of D that are being driven by some external entity. Now, latches don't have to have a clock per se. I mean, let's go back here. So I mentioned that this is a latch, but there's no clock in there. Well, there kind of is because the A is acting like the clock, right? It's just not called clock. It's not an explicit clock, right? So let's say I want to create a latch and a flip-flop. So the latch version of this will just say, if it'll say always at star, so we're pretending like it's sensitive to everything. But then I'm going to say if clock is 1, then Q gets D. And this is the flip-flop version where I say always at pause edge clock. If clock equals 1, then Q gets D. Right? So the difference is that one of them is level sensitive, meaning that whenever the clock is high, the latch will just give you whatever's in D. So D and Q, whatever's coming into D will pass through into Q as long as the clock is high. And when the clock is low, it'll block. It'll just retain the value, the old value of D, right? Now you'll notice that there is a bit of a delay here. So in this case, the clock is high and my D went high, and there's a little bit of a delay there, right? Because they're showing a propagation delay here, right? Even though in Model Sim or QuestaSim you wouldn't see that. But this is from the textbook. They're pretending like this is an actual hardware that has a propagation delay. So you can see clock is high, D goes high, Q goes high after a little bit of a delay. And then clock goes low, and then it goes back high, and then again, whenever D changes, Q changes. But then over here, clock is low, D changes, Q doesn't change, right? So in this case, clock was low, and this change in D did not reflect on Q, right? Because when the clock is low, it's like you kind of close it off, right? But on the flip-flop, on the other hand, the flip-flop is only changes Q on the rising edge of the clock. So whenever the clock goes from low to high, it's like it takes a snapshot of D and moves it into Q. It samples D. So the clock, the Q and the flip-flop will only change on the rising edge. So it changes on that rising edge, and it would have changed on that rising edge, but it didn't because there was no change. D was high there. Does that make sense? Okay. So what's happening is clock is rising edge of clock, D was low, so that'll cause Q to drop. Next rising edge, Q was high, that results in D was high, that results in Q going high. And then the third and final rising edge, D was high, but Q was already high, so there was no change. Okay? Make sense? So what happens in the CAD tools is that the CAD tools do a timing analysis to ensure that the time between rising edges is the maximum amount of time the logic has to propagate, right? So the tools have to ensure that the critical path delay is less than 1 clock cycle, right? Well, I'm going to talk. I have a lecture that goes into that in more detail later on. But my point is that the clock, in this case, with the edge-sensitive flip-flops, it makes it easier for the tools to guarantee that your circuit will work at a requested clock speed, right? Whereas with a latch, it'll do it, but you'll end up having to use a slower clock. Guys with me? So don't use latches. You don't want to use those. Sometimes you make them unintentionally. Okay. Anything else that I wanted to cover in the previous lecture? Okay. So now there's another thing that's kind of confusing here is the term register. So you guys, when you learned about flip-flop, you probably were taught that a flip-flop is 1 bit. It holds 1 bit, right? One binary digit. But when you design the architecture for your CPU, you're going to have flip-flops in there that behave exactly like flip-flops, but they're more than 1 bit. And when you have that, they're called registers. So a register is just a multi-bit flip-flop. It's implemented as multiple flip-flops that are in parallel with their clocks shorted, all connected. Right? So this way you've got like 4 bits in, 4 bits out, and on the rising edge of the clock, or falling edge, you can do falling edge too, the inputs are sampled and transferred to the outputs. Okay? Now, why is this confusing? Because you also have that term used in your assembly language, right? There's also registers in RISC-V assembly language, but they're not the same registers. These registers are digital logic building blocks, whereas the registers in RISC-V are architectural registers, which are actually implemented in a register file, which is a RAM. Okay, so you have to kind of interpret that term based on its context. You guys with me? So you have circuit registers and assembly language registers. They're different. Okay, so last time I talked about how to build these registers. By the way, if you build a register, you still use always underscore FF, which confuses things even more, right? So you're putting the flip-flop here in the Verilog code, but if Q and D are multi-bits, then it behaves like a flip-flop, but it's actually a register. It's a multi-bit flip-flop. Notice in this case they are. There's 4 bits. 4 bits, D and Q are both 4 bits. And then I mentioned last time is that you can have them resettable, enableable, depending on extra stuff you put in. You can also have things like this, where it looks kind of like a register, but it actually does more. This is a counter. So this has it's very short, 5 lines of code, but this thing is an up-down counter. So it has a reset, which is a synchronous reset. So if the reset is high, during the rising edge of the clock, it'll reset this 6-bit value to 0. If not, then if the enable up is enabled, it'll count up. If the enable down is enabled, the enable up is not enabled, right? So because this if statement is evaluated in order. So if enable up is 0, enable down is 1, then it'll count down, right? Which means if they're both enabled, if enable up and enable down are both 1, then it will count up, right? But if enable up is 0 and enable down is 1, it'll count down. And if they're both 0, then it just holds its previous value. You guys with me? So this thing, you can reset it, you can have it count up, you can have it count down, or you can have it hold. And notice there's no D input here, because now you could add a D if you wanted to have like another input that you could initialize it to some value other than 0. You could add that too. That would just go inside this always block. Okay?
I didn't catch that. If they're both 1, why is it not double drive?
Yeah, so this is something else that's always hard to explain, but so Verilog it has concurrent semantics, but there's some exceptions, and one of the exceptions is inside the always block. So if you write code like this, it's essentially building a truth table. Well, it's actually what it's doing is it's creating a Boolean logic for this. The way the Boolean logic is constructed is that it will assume that you as a programmer intended for 1, 1 to mean count up, just because the order that you put this if statement in, right? So it interprets this code and builds the Boolean logic from that. And so the code has sequential semantics like Java, C, and Python does, but not because it's being executed with sequential semantics, but because it's being translated into Boolean logic based on the description, which is in sequential semantics, right? Meaning that the order of the if then else is important, right? So it's kind of esoteric, but this is basically a shorthand for Boolean logic. What I should say, the next state logic in a state machine. Okay, so yeah, it's strange. Okay, so that was I talked about latches and I talked about flip-flops / registers. I talked about counter, but there's another type of memory. It's called a RAM. And so the difference with a RAM is that a register doesn't have an address. So it has a data in and data out, no address. It still has memory, but there's only one storage element in a register. But a RAM has this address input as well. which acts like a way to select one of multiple locations in the memory. Okay, now the problem with RAMs is that you can't initialize them without walking through each address individually and writing it, right? There's no global initialization, right? Well, that's not exactly true. On an FPGA, you can initialize them, but only on configuration of the FPGA. FPGAs are unique because, when you program them, you can also initialize RAM. So you can actually use an initial block for RAM. But in this class, we're going to have a RAM for the register file and a RAM for the instruction memory. The instruction memory we will initialize with your program, and so it'll act like a ROM, and then the register file will come up as uninitialized. So it'll come up as all X's inside simulation, and on the FPGA, it'll come up as all zeros because that's just the default for RAMs when you program an FPGA. You guys with me? Okay, so RAMs are usually described as having, they're described as a matrix or as a two-dimensional array, where the first number is the number of addressable locations, the number of rows. I think of it as rows. And the second number is the width, which is like the number of columns, right? So if you say a 1024 by 32 RAM, that means that there are 1024 addressable elements in there, each of which are 32 bits wide. So I think of it like 1024 rows and 32 columns. Make sense? Which means that in total, there's 32 kilobits in that RAM, but I can only access 32 bits at a time because there's just, in this case, there's only one address input, so there's only one port. So I can only access one element at a time. Make sense?
Yeah, but the assembler allows byte address, so are we gonna be able to do that?
Not in this one. No, that's a great question. Yeah, so that's one of the problems here is that when you think of computer RAMs are all byte addressable. I don't know why they're byte addressable. I think it's just historical reasons. I think IBM came up with that. IBM in the 60s decided that RAM was going to be, every address in a RAM on a computer would refer to 8 bits. They used to call them octets. Then they called them bytes. But you can't really store anything in a byte in this day and age, so it's kind of useless. It's kind of like pennies, But we've stuck with it. But in this case, since you're designing the hardware, you have flexibility to. In this case, this is not byte addressable. This is 32. This is addressing 32-bit elements. So if you wanted to make this byte addressable, then you'd have a problem because the only way to make this byte addressable, if you wanted to write one byte in here, you'd have to read the word that byte is a member of first, replace one of the bytes in that word, and then write it back, right? You guys with me?
So we're not gonna follow the conventional.
No, actually, in this class, we used to implement load and store instructions, and we had to deal with that. But we're not doing loads and stores. That was one of the things I did to simplify the class a bit. And then for the instructions will be word addressable. However, there are actually byte addressable in the instruction set. So we will have to fix that. We're going to make them word addressable. So we're going to change the way branch offsets are interpreted a little bit in RISC-V. You guys with me? So if you remember from MIPS, a branch offset was immediate in the instruction, and in MIPS you actually had to multiply it by 4 because it was a word offset. It was an instruction offset. So in this class, it's actually simpler. You just wouldn't multiply it by 4 and problem solved. So whatever offset you get from the assembler, it's already a word offset. Now in RISC-V, they changed that. And this is the crazy thing. RISC-V, they made the branch offsets units of 16 bits. So you have to take the branch offset in RISC-V and multiply it by 2. I don't know why they did that. I think they did it because they thought that, I think they were going to make a 16-bit version of RISC-V. Like ARM has a 8-bit version called thumb, the thumb instruction set in ARM. So I think the RISC-V people, I don't know if they did it or not, they might have done it, but the idea was if you have a really low-cost microcontroller, you know, like an Arduino style, you know the Arduinos have like an 8-bit processor. So the RISC-V people said, well, we should have a version of RISC-V that would work on an Arduino that would have really, like a really memory-constrained system, and the instructions would have their own special 16-bit encodings for that, right? So I think that's why they did that in RISC-V. They didn't do that in MIPS. But anyway, it's just something you have to be aware of. So addressability, what this address means depends on the width, is what I'm trying to say. So if it's a 10, 20, now by the way, how many bits is the address? Well, to get that, you have to take the log base 2 of the depth. So if there's 1,024 entries, the log base 2 of that is 10. So there's 10-bit address. Verilog actually has a built-in operator specifically for that called $CLOG, I think it is, right? Where you can calculate the log base 2 of something. Okay, so I think, oh, I already described this, sorry. But yeah, so the idea is that you treat it like an array, basically, right? So this is address 0, 1, 2, 3, and there's a width and a depth. The depth comes first, the width comes second when you're talking about the RAM, when you're describing the RAM. But keep in mind though, when you declare the RAM in Verilog, they're switched. So I remember I talked about that for the test bench, so I'll revisit that here too. So for example, if I want to create an 8192 by 32, 8K, 8 kilo entries, or is it kibi entries? I guess kibi entries technically, right? So 8,192 depth, 32 width. In order to create a RAM in Verilog, I would say logic 31:0 mem 8191:0. So notice that they have switched the order of these numbers. So this would be an 8192 by 32 RAM if you ask anybody, but in Verilog, these two numbers are switched. They put the width first and the depth second. Why? I don't know. This is wildly confusing in my opinion, but you just have to get used to that, okay? Okay, so the address is 12 bits. It's the log base 2 of 8192. And then I'm going to have read data and write data. Why 2? Why is there read data and why 2? One of them is for reading and one is for writing. So one of them is going to be the output of the RAM when I read. The other one is the input to the RAM when I write. Now, I don't have to have them both. I could just have, if it were like a ROM, I would just have read data, right, if I don't want to write to it. So your instruction memory in your CPU won't have a write data, just it will have a read data. But this RAM, I want to have the ability to read and write. And then I have a signal called write enable that will tell it whether I want to write. And a clock. Why do I have to have a clock? Because you have to have a clock for a RAM, at least for writing into a RAM. Not necessarily for reading. Okay, so the way I've implemented this is I've set read data is mem of address. So address is now treated as an input because it appears on the right-hand side of an assignment statement. So mem, address is an input, it's using an index for mem, and it's being assigned to read data. Now you might say, wait, what if I don't want to read? Well, you don't have a choice. This thing is always going to read. So whatever's on address, whenever address changes, it's going to activate this assign and update the read data instantly. So this has an asynchronous read, meaning that we don't actually have the clock involved in the reading here, right? There's no clock here involved. Now for writing, on the other hand, you have to have a clock. I don't think you can write without a clock to a RAM. If it's possible, I've never seen a way to do it. Every time I've seen a RAM, there's always been the writing process is linked to is controlled by the clock. So I have an always FF. Now you might say, wait a minute, why are you saying always flip-flop if you're making a RAM? I don't know. It's another one of those weird terminology things in Verilog. So they still use the always underscore FF, even though this is not a flip-flop, this is a RAM I'm building. Of course, I could put a flip-flop in this same always statement too. I can combine them. But in this case, I'm saying on the pos edge clock, if the write enable is asserted, then I'm going to put mem address on the left-hand side of the assignment statement, and I'm going to put write date in there. Okay, so the writing is synchronized to the clock, right? But the reading is not. So this is an asynchronous read, but has a synchronous write. Yes?
I think it has anything to do with the worst case, you know, the timing, that it takes longer to write, perhaps, or.
No, it could be. I don't know. I've never tried. I mean, if you didn't have the clock, it would, you know, you'd have to have a way to lock data in somehow. So I guess you could make a latch-based RAM maybe, but I've never tried that. I don't know if that would work. This is just this is the convention that's always used for RAMs. Okay, and then also, as I mentioned, there's this initial statement. You can initialize the RAM. This is the same syntax we used for initializing the test vectors for the test bench, but you can use it for RAMs too. Now, if this were an ASIC, you couldn't do this. This is one of the differences between an ASIC and FPGA. If you were building a chip, you would not be able to initialize a RAM on a chip, like an SRAM on a chip that you were having fabricated. But on an FPGA, you can, only because FPGAs have the configuration process where you put the bit stream in and you configure the FPGA. And it turns out that not only the logic gates and the interconnect are configured, but the RAMs are too, and the flip-flops. So that's one nice thing about an FPGA. But keep in mind that only works once when you configure it. Like you can't like reset the FPGA and have it, once you like, if you can reset the FPGA, but the only time you can initialize RAMs and flip-flops is through the lengthy programming process, which, how long does it take to program those? About 20 seconds, something like that? And that's a small, you know, bigger FPGAs take longer, but it's non-trivial amount of time to program it, because when you program it, you're just sending in one bit at a time. It's programmed it through a big bit, what do they call that? Boundary scan, one bit at a time through JTAG. It's like a big shift register, so it's very slow. And there's millions of bits that have to go in. Okay, any questions about that? So what this is like a convention, a coding convention, pretty much. Like when you write a RAM, you have to kind of write it in this style so that the synthesizer will recognize what you're trying to do, right? So a lot of SystemVerilog programming, at least the behavioral code, a lot of it kind of conforms to these kind of templates, right? But there is some flexibility here. Like for example, if I move in the write logic inside the always statement, like if I say if write enable, I'm sorry, not the write logic, the read logic. Sorry, the write logic was already there. The read logic. If I put the read logic in here, the read logic being the setting of the read data, this now becomes a synchronous RAM, synchronous read RAM, where it takes one cycle to read it. So before, it took 0 cycles to read. Now it takes 1 cycle. There's a 1 cycle delay if I want to read the RAM. Okay, you with me? Now you might say, why would you choose one or the other? Because real RAMs all have a synchronous read. However, there are other ways to build a RAM on an FPGA. You could make an array of registers connected with a mux, where their outputs are muxed, and that would create an asynchronous read, right? And there's also something called, on the Altera FPGA, they have these things called MLabs, which is where it uses the lookup tables that were normally used for logic. You can use those as a RAM, in which case you can get an asynchronous read out of those. But if you want to use the dedicated RAM circuits on the FPGA, which are called M20K blocks on the Altera FPGAs, you have to have it with this synchronous read. You guys with me? I know that's a lot. Basically what I'm saying is that depending on how you code this RAM, it will determine what physical circuits on the FPGA are going to be used when you put this on the FPGA, right? So there's a place and route process that happens where or not even play, actually it happens before that in the mapper. There's a mapping process that maps your code to physical entities that are on the FPGA. That's called the mapper. Actually on Altera it's called the fitter. But anyway, the point is you're going to use different resources on the FPGA depending on how you describe the RAM. Okay, so here's an example of a synchronous versus asynchronous. This is kind of hard to explain, but I tried to illustrate this, but it's a little weird. So I have a memory here where the contents of the memory are equal to the address. So address 6 has the value 6, address 7 has the value 7, address 8 has the value 8. That's how it's set up, okay? So you can see that on the top, every time I change the address, you see the address is 4, and then the read data is 4. The address goes to 5, read data goes to 5. There's no delay there. As soon as the address changes, the read data updates immediately. But over here on the bottom, check this out. You see how the 4 on the address becomes 4, but there's a shift. There's a 1 clock cycle delay. There's a phase shift. I put 4, but that doesn't take effect until the next cycle. You guys with me? So now I'm saying I want address 5, and the RAM's showing me 4. Why? Because it's going to show me 4 until the next cycle when it finally updates the 5 on the output. Make sense? It's kind of hard to see that, but the point is here is that if you have a synchronous RAM, a synchronous RAM with synchronous read, it's always lagging by 1 cycle for reading. It's always delayed. There's a delay in there. Does that make sense? Now this is going to have important implications in Lab 4, just to give you kind of a heads up, because our instruction RAM is going to be synchronous, which means it's going to take 1 cycle between when I give the program counter address to when the instruction pops out. Okay? That's going to comprise the fetch stage of our processor. You know, you guys learned about in 212, you should have learned about there's a fetch stage, right? And when I was in school and they said that, I was like, why do we need a fetch stage? What's the deal? What's the fetch stage do? It just reads an instruction. Why is there a whole cycle for that? Why does it take a whole cycle to fetch an instruction? Well, it's because the instruction memory takes a cycle to read, right? The problem is that if I have a branch instruction, I have an issue because the branch instruction is going to change the next instruction I want to read. But by the time I even realize that there is a branch instruction, I've already fetched the next instruction, right? Which is why branch instructions require a penalty. You have to flush the instruction you fetch, right? There's this disconnect between when you want a branch and when you can actually enact that branch, because there's this delay. It takes time to read instructions. You guys with me? Okay, but we'll get to that in the next lab. Okay, what about the register file? I brought this up earlier. Is the register file synchronous or asynchronous? What is it? What kind of RAM is it? It's a RAM. They call it a register file. See, again, the terminology is weird. So a register is not a RAM, right? But if it's a register as part of the RISC-V set of general purpose registers, then it's actually a RAM. Why? Because you can only access a certain number of registers at a time. You guys with me? It's weird terminology, but when you create the register file in hardware, you actually build it as a RAM because it's a RAM. It's a 32 by 32 RAM. Well, in a 32-bit processor. In a 64-bit processor, it's a 32 by 64 RAM. Okay? Yes?
Could you not make a RAM out of register?
Yeah, so that's what this does, I think, in the actual hardware. It creates I think it does. It actually creates an array of registers, but then it puts a multiplexer on the output, and then what they're doing is they're just selecting one of those registers with a multiplexer, and the address is going into the read address is going to the multiplexer. The write address is going to go into a decoder circuit, which is going to activate the write enable on one of the 32 RAMs, right? So yeah, you're right. I think that's how it's done. But if you look at the code is written in the style of a RAM, right? But it's got the asynchronous read. Now, why do we want asynchronous read? Why? Why do we want asynchronous read? Well, we don't need to have asynchronous read. But if you have a synchronous read, it's going to complicate things for our CPU a little bit. Now, you might say, wait a second, okay, if you remember from 2.12, there's the fetch stage and there's the decode stage. And the decode stage is a whole cycle that's allocated just to reading the registers, right? You guys remember that? The problem is that, here's the issue, is that that's fine, except that branch issue I talked about earlier. What is generally done, at least in MIPS and RISC-V, is because branch instructions have this weird delay, right, where you have to fetch a branch, realize it's a branch, decide if you're going to take the branch, and then try to change the program counter, and by the time you do all that, you've already fetched a whole bunch of instructions that you didn't want to execute, right? Because of that problem, usually the branch resolution logic is pushed back into the decode stage, which means that we want to have the registers available asynchronously. We want to be able to get, once the instruction is fetched, we need those register values as soon as possible in order to be able to resolve the branch as soon as possible, right? So in this class, we're going to make this register file asynchronous simply because we want to resolve branches in the second cycle after the instruction is fetched. You guys with me? Now there is, again, we could change it, but this is designed to make things simpler. So what does that mean is that the read logic is outside the always FF. You guys with me? Now you could put the read logic in an always at star or an always com if you want, but I just put them, like I said, I try to avoid always, I try to only use always for memory, unless, like I said, except for the control unit. You guys with me? So what's going on here? Well, in the register file, it also is unique in that there are 3 ports on it because we want to be able to read 2 registers and write 1 register at the same time. Why? Because that's what the instructions do. The instructions, the MIPS and RISC-V and all the RISC architectures follow what's called a 3-address architecture, meaning that you have 2 operand registers and 1 destination register. There's 3 registers specified at most, sometimes less, but at most there's 3 registers, right? This was not always the case. In fact, the x86 architecture is a 2-address architecture. And if you write code for an Intel machine, you only specify 2 registers. The first register is used, it's used as both the first operand register and as the destination, right? But when the RISC architectures came out in the early 80s, they wanted to use a 3-address architecture to facilitate pipelining, which means that the register file now has to have 3 ports, meaning that I have to be able to access up to 3 registers in 1 cycle at the same time. However, only 2 of those ports are read-only ports, and 1 of those ports is a write-only port. So you can design, so now I've got read address 1 and read address 2, which allow me to read 2 registers at the same time, asynchronously, which are spit out on read data 1 and 2. And then a third, optional, is I could put a write address in with the write enable and write data to write a 3rd register. So I can read 2 registers. Actually, I always read 2 registers because I can't control that. You're forced to always read the registers addressed by read address 1 and 2. But you can optionally write a 3rd register, right? Now you don't have to, I mean, RAMs, you can have ports that can read or write. But in this case, these 3 ports are specific to, reading or writing, depending on the port. You guys with me? Now you might say, what's that other crap in there? Well, there's some other stuff in here too. By the way, we're going to give you this. This is the same register file you're going to use in your CPU. We're going to well, not, we have a slightly cleaner one that we're going to give you, but this is basically, this is the register file you're going to use in your code. What is all this crap in here? Okay, so in RISC and in MIPS, if you read register 0, you always get the value 0. The problem is that there is a register 0, which you can write to. But the circuit prevents you from reading it. So you can write to register 0, but if you read from it, you don't get what's in there. You just get it bypasses it and gives you 0, right? Additionally, there's this other weird thing that happens in a pipeline processor. The register you're writing is happening in a different instruction than the one that's reading, because the reading of the register file and the writing of the register file are happening in 2 different pipeline stages. So when you use this, so you have one register file, but whatever is coming in from write address is the instruction that's in the write back stage, and the read addresses are coming from the instruction that's in the decode phase, right? So you're accessing these 3 registers, but they're coming from different instructions. And in fact, the one that's writing is an instruction that appeared earlier in the code, right? So the writing instruction is an earlier instruction. It's an older instruction. It was fetched earlier than the instruction that's reading. Okay, so what ends up happening is that if you write a register and then you subsequently read that register in a later instruction, so I write and then I read, which happens a lot. It happens constantly, actually, right? You're always writing and then reading. Every time you want to calculate sub-expressions of a complex, like even in the code I showed you in the quiz, all that addressing stuff, I'm always writing and then reading, right? So this code is designed to create a bypass path where if I write a register and I read the same register, normally the reading would get the old value of the register, right? Why? Well, because the reading is asynchronous, but the writing is still synchronous. So it still takes a cycle to write, but it takes 0 cycles to read. So if I'm trying to read and write the same register at the same time, the reading is going to win. It's going to happen first, because my read is instant, but my writing is delayed by a cycle, right? So that's a problem, because in the RISC instructions, if you have a register that writes a register and then a following instruction reads it, the following instructions get the old value. It's not going to get the updated value, right? This creates a data dependency. So what this code is doing here is it's checking to see if my read address equals the write address and if I'm also writing, if my intent is to write. And if that's the case, instead of reading the RAM, I bypass that and I just forward the write data, right? So this is going to create an internal multiplexer that's just going to say, if I'm reading and writing the same thing, take whatever is writing and just bypass the RAM with that. Don't take what's in the RAM, because you're going to get the out-of-date value, the old value of that register, right? Does that make sense?
I didn't think that's the way that the processor worked. I thought that it forced the delays in there.
Well, that's another approach.
When that happens.
That's another approach. So another approach would be to not do this, right? And then have the processor at runtime detect this and inject a stall, inject a bubble or a no-op. You could do that, sure. Or you could tell the compiler to do that. You could just say, hey, compiler, keep in mind, I wouldn't put 2 dependent instructions next to each other if I was you. If you have to, put a no-op in the code, right? So the compiler can handle this, or the processor can handle this, or the register file can handle this. And in this case, we choose register file, right? Now, what's the downside of this? Is there a downside of this? Yeah, this adds significant cost to the register file in terms of area and in terms of delay. This is going to lengthen the critical path delay of the register file, which hopefully this isn't the bottleneck. If it's the bottleneck, this thing is determining our clock speed, right? But I don't think it's the bottleneck. I think the ALU is the bottleneck. I don't know. I don't remember last time I checked that. I don't know what the bottleneck is. This might be the bottleneck. In fact, if it weren't for this, maybe our CPU would run at 100 megahertz or 200 megahertz. I never actually looked into that. That would be a cool thing to check. But we put this in to make it simple, but there is a downside. There is a trade-off going on here, certainly, right? Yes?
I have a question about the RAM. So I know that FPGA has like some dedicated RAM on board that it uses whenever like an outdated RAM or anything. So just a question about that. Is that onboard RAM, is it DRAM that just gets automatically refreshed by the FPGA so we can treat it as SRAM?
No, it's actual SRAM. Yeah, that's SRAM. It's SRAM, and the RAM, they're called M20K, so they're 20 kilobits. So the RAM primitives are fundamentally, they're 1,000 rows, 1,000 entries deep, and they're 16 bits wide, or no, 20 bits wide. 20 bits wide, 1024 entries deep, so they're 20 kilobits. But the cool thing is that if you want a bigger one, they're automatically arranged for you in an array. So you can have a wider one, in which case it puts two RAMs next to each other, or deeper, in which case it puts them down, right? But if you want to go smaller, like say I only want 1,000, let's say I only want 512 entries, then it actually just uses half the actual RAM. So depending on how you size your RAMs, you may get an inefficient usage of the RAMs on the FPGA, right? Usually no one cares about that because there's a lot of RAM, but yeah, that's the physical. There is a physical size of those RAMs versus this, which is a logical size that you pick.
Physical
Yeah, 6 transistors per bit. Yeah, it's RAM, it's SRAM. Yeah, you can't mix DRAM and logic on the one chip.
Okay, yeah.
People have been trying to do that for 40.
Automatically refreshing it so we don't have to worry about that or something.
Now mixing DRAM and logic on one chip has been a holy grail. People have been trying to do that for 50 years. If you could come up with a way to do that, that would be, to create a true processor in memory, that would be revolutionary. That would break the memory wall. But no, this is just SRAM, which means that it's 6 transistors per bit, which means it's it's not very dense. So the RFPGAs have, I don't remember, I want to say 128 kilobytes of RAM, so not much. Yes?
Is the instruction register, the instruction RAM we're gonna write, is that the instruction cache, basically?
Yeah, so
Are you gonna define how large our instruction cache?
yeah, we're going to make it 4K deep and 32 bits wide. Yeah, we're just going to lock it in. I used to have an instruction cache in a very early version of this class, but it was tricky because you have to create a controller for that'll service cache misses, and it could be done. We have a DRAM too on the board. We have 128 megabytes of DRAM on these boards. But again, that was one of the things I did to simplify the course. We're just going to stay on chip. Okay, let's see. Well, that actually worked out pretty well. I think I covered. Okay, so next time I'm going to talk about the ALU that we're also going to give you. And then we'll start getting into what instructions we're going to implement.